Hello, everyone. So I'm going to talk about some results that were either led or enabled by observations taken at Keck. This is a list of some of the results I'm going to highlight here. So first of all, I'm going to talk about the interstellar object stuff. So I think it's pretty apparent for a room full of a good number of exoplanets this year, and as well as people studying previous, that the solar system is not a typical case of the outcome of the planetary formation process. We see, for example, debris that are way more extended than the original debris of our solar system, as well as planetary architectures that are much different. So what the interstellar objects are giving us is the opportunity to study the outcome of the planetesimal formation process around other stars that would otherwise be inaccessible from observations from active star, from mining star. So this is the first two interstellar objects, one-eyed and two-eyed Borisov. The interstellar object is defined as one which has an eccentricity significantly above one and a very large E of infinity. So the first two had eccentricities of 1 to 0.2 to 3 and E infinities of around 30 kilometers per second. Compare that with a comet Bolin, which had eccentricity of just 1.06, which was a hyperbolic comet that had a close to kind of a Jupiter. So these are objects that are very clearly have a larger eccentricity, much greater than one. Very quickly, these objects exhibited very different physical properties. Oumuamua had a non-comet-like appearance and very large light curve amplitudes, indicating an elongated shape. Whereas two-eye Borisov had a more, let's say, conventional comet-like appearance. But we also were able to observe this two-eye object with Keck optics, and it has a diameter of about a kilometer or less, whereas Oumuamua had a size of around 200 meters or so. But there's a new sheriff in town, Three-Eye Atlas, which was discovered July of this year, which has the greatest eccentricity of all known interstellar object of around 6 and a V infinity of around 60 kilometers a second. That was discovered by Larry Deneu using the Atlas telescope in Rio Cortado in Chile. And we jumped on it quickly right away. I think this is the first peer-reviewed publication of this on this object published on July 18th. And we've got some visible imaging multiple bands, which show that the object has a somewhat extended appearance and colors, which are significantly more red compared to most solar system objects, including other interstellar comets. More recently, we got some deep imaging with Gemini, and now it exhibits a more, let's say, typical comet-like appearance with the anti-solar tail. We thankfully, to the generosity of the Keck directors, we were granted the time to observe the comet Mossfire on July 11th, and we got pretty good YHA-HK imaging. It was in a very crowded star field, as you can imagine, quite a lot of stars to be observed with a 10-meter telescope with the most powerful red camera on the planet. But it was pretty awesome conditions. We also were able to get some spectra there, and so the spectrum more or less looks flat, there's no evidence of absorption, which is typical for a micron scale like dust like comets. So more recently, we got just a couple days ago, September 15th. I'm showing this from Gemini, but I want to show you that we just recently detected some interesting cometary gases, diatomic carbon, triatomic carbon, and of course the booming Sagittarius line, which is already known. But I think this is the first time you see some of these other cometary volatiles. So I'm going to move on and talk about some other interesting objects that we observed. These are the kind of exotic type asteroids found in our solar system. So late last year, there was a potential impactor was discovered again, also by Larry Deneu with Atlas and the guys by a street group. This object, when it was discovered, had an Earth impact probability of about 4%, and that's the largest we've seen for a comet since Apophis in the early 2000s. And this asteroid was about 60 meters in size, which gives it a danger rating combined with its higher impact probability that is quite concerning. It was discovered in late December of last year, but the predicted impact would occur not for several more years. That impact probability has basically dropped to zero with the Earth, but there is now a non-negligible lunar impact, 1 in 25 chance of happening in 2032. And this can still be quite concerning because it will produce a goodly amount of debris, which could interfere with our geocentric satellites. Thanks to visible near infrared colors attained with other telescopes and as well as Keck, we now know the asteroid is an S-type asteroid. It's about 60 meters in size because the taxonomic type gives you some estimate of the size. And we now know it has a shape roughly resembling a hockey puck on the right here. This is a nice video that was made by the press office at Keck Observatory. So I'm also going to talk about a couple of other objects called mini-moons, which are these temporarily captured asteroids. There are only a few known, but I'm going to talk about one called 2020 CD3 and another one that was recently discovered called 2024 PT5. And these are objects that come within the Hill sphere of the Earth and are captured for a non-negligible amount of time and actually have geocentric orbits, that is, geocentric eccentricities less than 1. So these objects typically have an orbital lifetime of about 300 days and completes on average about 3 revolutions around the Earth. And the first was known as 2006 RH120. But in 2020, the second one, there was quite a long drought. 14 years later, the second one was found, 2020 CD3. These are images taken with ELRIS. Very good image quality. This is Christopher Krumke. These observations is really nice observation in all 6 bands with ELRIS. And what's interesting is that the spectrum resembles lunar rock, not lunar soil, not agglutinates, but actual lunar core samples. It actually quite resembles lunar core samples that were brought back from Apollo. And recently, towards in August of last year, the third mini-moon was discovered, again, by Larry Ledoux Atlas Telescope. Amazing year for this guy. Interstellar object, moon, and impacting asteroid. And so this was captured for quite a bit shorter duration, around 60 days. But we did get a spectrum removal combination with other telescopes in Keck. So we got using Mossfire, we got the near infrared YJ observations. And these visible and near infrared spectra combined together looks again like lunar rock. So it's an emerging picture here that these temporarily capture-like objects, the dominant source of which is the moon itself. So it's kind of opening up our minds about what can be the source of other sources of asteroids in our source. So another, let's say, exotic type asteroid I'm going to call is this large non-gravitational asteroid. And what exactly does that mean? Well, I'm going to talk about this one in particular called 1998 KY26. It's about 30 meters in size, 11-minute rotation period, and it's a rendezvous target of the Hayabusa 2 SHARP mission, which is good because it basically is going to test if my measurements were correct. You better get it right if spacecraft is visiting to it. But what does it mean to have a high non-gravitational acceleration? So this is a plot that, as a function of absolute magnitude on the x-axis, shows on the y-axis the acceleration on the non-gravitational acceleration imparted on an object's orbit. So all the objects which have a large enough non-gravitational acceleration can be described by the Yarkovsky effect. That is, thermal recoil forces are all in blue there, lying across this blue line. But then there's these objects which have non-gravitational accelerations, which are much more significantly larger than those that can be described by thermal recoil forces alone. So these have been given the name dark comets, but I think it's a misnomer because I don't think they're comets. I think something else is going on here. But they have non-gravitational accelerations that are in far excess of thermal recoil, so there must be some other mechanism that is imparting momentum on that is accelerating the orbit such that it is more accelerated than the Yarkovsky described by the Yarkovsky effect alone. So we can keep imaging of this object with the Keck. And we found that the imaging was sufficiently sensitive enough that you basically eliminate dust as being an emitted source of the potential non-gravitational acceleration for this object. Is that if there is dust being emitted by this object, it must be large enough that it is not detectable directly from our ground-based observations alone. So we also observed this flyby target of loose emission called Binkanesh, which means you are marvelous. And its 850R observation showed that it had an S-type spectrum, a diameter about 850 meters diameter, and was actually the motivator for the Lucy mission doing a little detour to actually go look at this thing. And when it arrived, it found this. It found the first binary asteroid. So this is the face-on view of the Lucy observations of the Dig system. But when viewed side on, you can see what it means by binary. That you have Big Nash moon body there, but the binary is kind of a peanut looking thing. It's actually two asteroids stuck together like a peanut. So it's the world's first known binary asteroid. And so this is a list of all the results I just described, and I'll take questions if you have them.